Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's make a start. So, yesterday when we finished up, I'd shown you some mystery QQ plots, right? Data that had different features and what does the QQ plot look like. So, hopefully by now we're all feeling confident that QQ plots are things that we can use to determine whether the data is normal or not. Or if it's not normal, what is it? Okay, there's a couple more things to say about QQ plots, and then what I'm going to do is move to talking about comparing distributions, which brings us closer to the sort of thing you're going to need to do in the assignment. So my goal is that at the end of today's lecture, you'll have all of the techniques you need for that assignment, all right? So that's my goal. So what I'd like to do in every lecture, if I could, is dedicate a little bit of time to looking at some fun stuff, but I've been trying to just make sure I cover the material so you have as much time as possible to do the assignment. So starting next week, I'll try and integrate some more fun stuff in every lecture, okay? All right, so QQ plots we did yesterday. Let's just have a quick look at an example again. So we looked at normal data. So if I go X is R norm, 1000, 0, 1, and I do QQ norm of X, I get that plot. And as we talked about yesterday, if this thing looks like a straight line, then you're good to go. Okay? That is, there's evidence that the data is plausibly normal. Now, you know, dead straight is one thing. With real data, you never get dead straight. Okay? Data has variation, little bumps and wriggles. So you always expect to see something that's a bit like this. This is with a lot of data. It's with 1,000 data points. Okay? I mean, I could up the ante and put in 100,000 data points and you still get little bumps and wriggles. Not as many, but they tend to occur out here in the tail. Okay? They tend to occur out here in the tail. And if you think about it, you know, 99.7% of the normal distribution sits within plus or minus 3 standard deviations. So you can have 0.3% outliers. And if you've got 100,000 data points, 0.3% gives you a few outliers. And that's what those tailing points are. Now, the other thing that happens with QQ plots that you've got to be real careful of is this is what you get when you've got a lot of data, okay? Patterns are easy when you've got a lot of data. When you don't have a lot of data, life can get a bit harder. So, for example, let's generate some small data sets, and again, you can watch me generate it. 10 data points, 0, 1, and that's what you get. Now, what's the shape of that? Is that linear? No. Looks, what shape would you say that distribution is based on that picture? So that's curved. What's the distribution shape? When a QQ plot's curved, it means the distribution is skewed. Yeah, skewed. Skewed. I could just hear just about all to say it. Skewed. Is it skewed to the left or the right? Curves up, skewed up is right, skewed to the right. So this is normal data. I generated it as normal data. It looks skewed to the right. There's only 10 data points. Let's have a look at the histogram. That doesn't look too normal, does it? Right? It looks skewed to the right, and that's what the QQ plot's telling you. But that's with 10 data points. So, you know, the truth is this. If you've got 10 data points, good luck, right? You can pretend it's normal, but you ain't going to know. And you ain't going to get a QQ plot to tell you that necessarily. sometimes it will be, sometimes it won't. You know, we can generate lots of different small normal data sets and you'll get every shape under the sun, right? You can see them. They curve up, they curve down, they make S shapes, they make little bear shapes, they do whatever they want. It's 10 data points, okay? So there's always a challenge when you have very small data sets about what to do. The truth is if you've got 10 data points, you're better off just praying, right? Because the data does what the data does when you've got very small data sets. And you kind of have to trust that your normal theory kind of works. Okay? We talk about we live in the age of big data. We do. Many, many data sets are very large indeed. But, you know, the truth is many data sets are actually still very small, right? So I do some work with a physiotherapy lecturer at Macquarie, and she looks at knee pain, okay? So she has real people come in and they do things, you know, they stress their knee joint and all that sort of stuff. We deal routinely with samples of 9 people, and we follow those 9 people over 2 years. Getting people to agree to it is not easy. There's pain involved, right? Not only that, we get people who are lost to the experiment because they go off and they have knee replacements and stuff like that, okay? So small samples still exist, and, you know, it doesn't matter how long you live. Big data doesn't mean every data set is big. It just means that some are, right? And in fact, there's actually this notion now that the words big data are actually very poorly chosen. It isn't that data's big that's the problem, it's that data is complex, right? And it's not so much that there's a lot of data, but that there's a lot of variables typically. And so a common problem in statistics these days is that you have many, many more variables than you have data points. And that's a problem, because every regression class you ever sat in requires that n, the sample size, be a fair bit larger than p, the number of regression variables you've got. And that's breaking down in modern statistics, right? So there are all these issues. So you will have to deal with small data sets. When you look at the assignment, you'll notice the data sets are not big. And so you'll have to deal with that. And dealing with that means making judgments, okay? So here's the other thing I'll say about the assignment is don't be afraid to make judgments. I mean, that's basically what you're being asked to do. And if you ask me, what should I do about this? My answer will typically be, it'll sound unhelpful, but it'll typically be, well, you've got to decide that. That's yours. You own that, right? And that's not me being mean, because if I was mean, I'd say mean stuff as well, along with it, you know? But it's really just me saying, look, making judgments is part of the deal when you're dealing with data, okay? This ain't a math class. In math classes, at the end, you get an answer, you can turn to your mate and say, what did you get? And if you get the same number, you're probably both correct. Or both wrong, but probably both correct. In stats, that just ain't so. There's a lot of judgment involved. And I want you to make those judgments, okay? All right, one more thing about QQ plots. You'll notice that the QQ plot I've got on the screen is about as wide as it is high, and that's deliberate, because QQ plots look best when they're square, okay? We're comparing two things one with another. We hope that the scales are roughly equivalent or proportional, and so square QQ plots are best. So I've arranged my window so it's more or less square. It's not exactly square. I can force it to be square, and I'm going to suggest you always do this. So when you're constructing QQ plots, you're generally going to set par PTY equal to S. That's square, S for square. Then when I do my QQ plot, you'll notice it is actually square. It is exactly as high as it is wide. Okay? I think it's always a good idea to add the reference line, and there's a command for it, QQ line. That reference line should have an intercept equal to the median of the data, and it should have a slope equal to the standard deviation of the data. Okay, that's how QQ line works. And that gives you an idea of how close to a straight line your QQ plot is. Okay? So always put that in. If you want to, you can put in those axes, right? Remember I was putting in axes yesterday, but I'm going to show you a way to make it look nicer. So the axis that goes vertically will be at 0. So v equals 0 will give you that vertical axis. Why 0? Because 0 is the middle of a standard normal, right? But what I'm going to do is AB line v equals 0, but I'm going to make it grey. The reason I'm making it grey is I don't want it to be black like the other lines. I want it to be a little bit understated, okay? So I'm going to go AB line v equals 0, colour equals grey. See how that sort of looks a bit nicer? Doesn't dominate the plot. And then I'm going to put the horizontal line in. Where you put the horizontal line in is a bit harder because your data may not have mean 0, okay? The data I've generated here is supposed to have mean 0, but it might not exactly. So rather than putting h equals 0, I would suggest you put it at the median. So you're doing a QQ plot of x, so h equals median of x, and again, make that one grey as well. Whoops. Okay, you'll see that goes pretty much through the line. Not exactly, because QQ line uses a slightly different algorithm, but that's okay, it'll be close enough. All right? Now, what else can you do just to make this quote-unquote perfect? The title for a QQ plot that's normally given is normal QQ plot. That doesn't tell you anything about the data you're using, so I would probably give it a title that's better than that. Okay, so I'd go right back to the top. I'd go QQ norm of x, comma, main equals, and then you put your title here. This is your favourite title. So you'd probably want to put, you know, QQ plot for distribution of whatever it is, heights. Okay, that changes the title. Then you go back through and put all your lines in. And of course, you know, if you've done all this in the script editor window, it's easy to edit and fix. And there you've got your QQ plot. Okay? Now, neatness matters. Okay? I want every plot to have a title. I want every plot to be labelled. I want, you know, a QQ plot without a reference line is like a newsreader without a tie. You just think that's sloppy. I don't like that. I don't know why ties are good, but people like them, right? So you've got to make things look presentable, okay? Every graphic you produce that you give to someone else, whether it's me or your boss in a future life or whatever, should speak to your professionalism, okay? You hand sloppy stuff in, guess what happens? People form a view about you. And here's a secret. Once someone's formed a view about you, it is really hard to change it, right? If someone thinks you're ugly, guess what? You could go to you could go and have plastic surgery, you could fix everything up, but they're probably going to still believe what they first believed. First impressions matter. So try and make a good impression. All right. Okay, so with all this in mind, let's now have a look at the QQ plot for the intermediate star data. So before we do that, okay, I don't want my next plot to be square, so I'm just going to scrub the plotting surface. I'm going to hit the broom and clear that out. Okay. We've looked at a histogram and we've also looked at densities of the intermediate star data. So there it is. Okay. We've all kind of agreed it's skewed to the left. Yep. So what's the QQ plot going to look like? It's going to be curved, and the curve is going to go down, right? Left, down. Okay, let's see if it does. So now, again, good hygiene, right? Good hygiene means you redo all this stuff. Par PTY equals S. Okay. QQ norm, inter, main equals, and then, you know, QQ plot for intermediate star data. Right, so title that's meaningful. There it is curved. Okay, QQ line of inter. Okay, then we put in our vertical line. Then we put in our horizontal line. It's going to be at the median of inter, isn't it? Done. Now you'll notice that crosshairs misses the QQ line. That's okay, doesn't matter. Just gives us a rough reference for the middle of each distribution. Okay? And you can see the curvature on this. Okay, you can see that there's a big tail down this end, these things tail away quite a lot, and so on. We made the plot square, but don't expect the QQ line to be at 45 degrees, right? It'll only be at 45 degrees if everything's good. Here things aren't good, right? This thing's not normal, so you don't expect it to be at 45 degrees. And this is more or less what we expect. Okay, so that's pretty cool. All right, so what do we do next? We've gone on a bit of a journey, right? Our journey has been to look at essentially the genesis of where histograms come from, where densities come from. We've then moved to QQ plots because densities as a picture of the data are quite evocative, but they don't really help us decide on normality very easily, so we've got a tool now that helps us decide if our data is close to normal. If you're reading the notes as an accompaniment to us chatting away together, then there's also covered CDFs, so cumulative distribution functions, symmetry plots, those kinds of things. Okay? A question you might ask me is, what do we use in the assignment? Okay, good question. You use whatever tools best summarise what you think is going on with the data. So you can use anything among the things we've talked about. If you want to, you can use stuff we haven't talked about. That's okay. Now, if it's not effective, that's not going to be good for you, okay, but the choice is yours. Truthfully, you don't want to throw the kitchen sink at this. So a question came up yesterday, this question comes up every semester. How many graphs should I put in? And I gave my usual unhelpful answer, which is, how long is a piece of string? So how long is a piece of string? Answer, however long you want it to be, right? So how many graphs do you put in? Many as you want. Now you've got 4 pages, so you ain't going to be able to put in 10 because they ain't going to fit, right? And I will make the observation that despite the fact that I'm 6'5", I do understand that small is better, okay? So the smallest number of graphs that tell the story of the data is what you're aiming for, okay? So that probably doesn't mean 1, because 1 graph can't possibly tell the story of the data, but it doesn't mean 10 either. So the answer is in between, and make judgments. Make a judgment, okay? If I think you've done too many, then you won't get as many marks as if I think you've done the right amount. And you know, this isn't like the secret sauce that McDonald's puts on a burger. There is no right answer. There are wrong answers, of course, but the idea is for you to communicate effectively. So, for example, there'll be some answers to the assignment for which, you know, say 4 graphs is the right number because it's supported by an argument that uses and needs to use those 4 graphs, right? There might be another assignment for which 2 graphs is the answer because the writing around it is supported by those 2 graphs and the story is told. So it's this combination of graphs and story that you need to weave, okay? So there's an art to it, and there's a lot of judgment involved, and I get that. And it's not something for which I can really be apologetic about, because once you hit real life, it's simply expected that you'll have that judgment sorted, right? So you don't want to be sitting in your first job next year asking for instructions, because that ain't going to play out well for you, right? You're much better off having played the game around making judgments earlier on, and that's what we're trying to do. Okay, what we're going to do now is we're going to try and move to comparing distributions, which is kind of where we've been headed all along. But in order to head there, we had to think about one distribution initially and try and work out how do you display one distribution. So we have 3 different distributions here. Remember, there are 3 different kinds of stars. There's disk stars, there's intermediate stars, and there's halo stars. These are the 3 different kinds of stars, okay? So let's try to compare these 3 distributions, okay? And we're going to do it in a really simple-minded way to get started. I'm just going to do this. I'm going to go hist of disk. So I'm going to show you a histogram of the disk stars, okay? So you can do it on your own computer there if you want, or you can just look at the screen. There it is, okay? Oh, plots are still square. How do I make plots stop being square? I hit the broom, okay, and do it again. Let's do it again, so they're not square. There's a histogram of the disc stars. Okay, so have a look at that. All good? Make a judgment, think about it. What's important for distributions, okay? So let's think about that. Anyway, we'll move on. Inter, there's the intermediate stage. I've seen that one before, so I don't need to leave it up for very long. Okay. And halo. There's the halo stars. Have a look at that. All right. We've looked at all three. I've given you all the information you need to compare them, right? Showing you each of them in turn. It's cool. All right. Just so you know how after you eat a meal with garlic in it, you have some lemon sorbet or something to clean your mouth out so you can taste the next thing? So we'll just scrub the screen. It's like eating a lemon. It's all good. Okay, now you tell me. What's going on with this data? How do they compare? Last one was right skewed. What about the intermediate one? Left skewed, because we looked at that before. What about the disc one? Who can remember it, by the way? Who can't remember it? It was a couple of graphs ago, right? Yeah, it was kind of symmetric, a bit funny looking. Okay, that's cool. So what I'm hearing is that we kind of got the shape, right? So we got something that's symmetric, maybe a little bit skewed, hard to tell. Second one was definitely left skewed, third one was definitely right skewed. Okay, cool. All right, that's good. It's good. Where were they, by the way? Was one to the left of the others, to the right of the others? What do you think? So we know the intermediate stars kind of, 0 was kind of where they were, so we talked about that. Where were the disk stars? It's gone now, isn't it? Bugger. What about the halo stars? Where were they? No one's got any idea, right? You've got your computer in front of you, you can cheat. You can look back. But it's gone. Oh, no. Okay. So now you're thinking, oh, I wish I'd looked more carefully. I saw the shape, that was cool, but I couldn't tell where they were. All right, okay. Let me help you with that. I'm going to put all of them on the screen at once, okay? So let's do that. Let's go par MF rho equals C 1 3. Oh, no, 3 1. Oh, 1 3. Whatever. 1 row 3. Yeah, that'll do. I've got to put three on the page, okay? Let's do that. So I'm going to go boom, 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 side by side. Sound good? Yeah? All right, let's do it. Hist disk, hist inter, hist halo. Let's put them all on at once. Oh, except without the error. Oh, bugger. Let's just do that again. I'm incapable of typing a line without an error. It's just one of those things. There they are. Okay. Okay, so now we see the shapes. They're all in front of us. This is cool. Do we like this picture or not? No? What's wrong with it? Sorry? What? Too tall? No such thing as too tall. Well, let's attack one problem at a time. It's too tall. I don't agree that things can be too tall, but whatever. I respect that view. All right. No better? Okay. All right, that's nice. That does look nice. I do agree. Okay. So, roughly symmetric, roughly left skewed, roughly right skewed. Okay, we're good. Are they located to the left or right of each other? Can we tell? Bit of a complex judgment, isn't it? Right? Bit of a complex judgment. This one seems to be centred around 0, pretty centred. This one's 0 is sort of here, but there's a big left tail. It goes between -300 and +100. This one here, it goes between minus 150 and plus 100. This is smushed up, right? And this one here, it goes from minus 100, so it sort of starts where this one is only about here, and then it goes on only to 200, which is beyond this one. So if you look at those axes, you can tell where they all are, but gee, it's complicated. You've got to look at all those numbers, then you've got to do a little bit of mental gymnastics around where these numbers are. So minus 300's down here, and plus 200's up here, 100's here, 0's here, 100's here. And it's not visual anymore, right? Because you've got to think about numbers, so you're engaging two parts of your brain, the part that looks at pictures and the part that tries to work out order between numbers, and they're fighting with each other like they always do. What do you do? Okay? Now, one of the things that's preventing us really getting this looking really good is that you have to look at the axes. So maybe what we ought to do is put them all on the same axes, right? That's a good idea, right? Let's put them all on the same axes. So let's work on that. Okay, so let's start by going hist of disk. Now we need a set of, oops, I'm not typing in there, let's try it again. Hist of disk. So what axes will fit everything? We know that minus 300 will take us to the bottom of this one, and we know that plus 200 and maybe 50 will take us to the top of this one. So I need something that goes roughly between minus 300 and about plus 250. That'll be big enough to fit everything. Okay? So let's go xlim equals c minus 300 up to plus 250. Okay? And you're all pretending that I'm titling everything, right? Because that's what you have to do. I just don't want to do it because you don't want to watch me make mistakes typing, do you? Okay, so there's the first one. Here comes the second one. So instead of disk, I'm going to use inter. So I'm just forcing the same axes for each one here by using xlim. And now let's do halo. So here they all are. Boom, boom, boom. Okay, so now we get a bit of a sense of what's going on. They're all on the same axes. You can see that the disk stars are all sort of bunched together in the middle, right? You can see that the intermediate stars are sort of got a long tail on one side, but they're spread apart a lot more than the disk stars. You can see that very clearly because the disk stars are all in here and the intermediate stars are much more spread out. And then these are shifted. These are shifted to the right and they're spread out as well. And it's a bit hard to tell whether this is more spread out than this because of the alignment. They're next to one another, right? Now, I can probably do even better because by putting them next to one another, I'm trying to compare this to this to this, and I'm moving from left to right across the page. What if I lined them up vertically? And then I could just look down the page and I could see them shift, right? Middle, right, left, right, okay? And that's going to be better. Now, let's do that. So how do I do that? So first I'm going to make it tall enough so it can happen, okay? Because tall is good, we can all agree. And I'm going to make it skinnier because I don't want them to be fat, right? That's fat with a pH. Okay, so now how do I do that? I go par MF row, not 1, 3. 1, 3 means 1 row, 3 columns. I want 3, 1. 3 rows, 1 column. So 3, 1. Okay, and then I put my graphs on the page, one after another. And there they are. And I can make this a little bit skinnier so it looks even prettier. And there we have it. Now, this graph gives you your best shot if you're going to use histograms to compare these three data sets. And we've made a lot of choices on the way to here, okay? So, hopefully, the penny's dropping now about why this stuff is so damn hard, right? You might come into a course like graphical data analysis and go, I'm going to learn histograms. That is so easy. I'm going to get an HD. But then there's all these other things that come in, right? So let me tell you, if you do the assignment and you give me histograms that are all higgledy-piggledy over the page, just one after another, don't think about the axes, don't think about the alignment, you'll get a mark. Won't be a good one, right? So you've got to think about all these things. So, if you're going to use densities, what are the lessons we've learned here? Well, first of all, use the same axes as you move from plot to plot. Because if you want to compare things, you want as many things between the plots to be the same as each other, right? So having the axes the same means your brain doesn't have to do any post-look calculations around width. Because if the axes are the same, you can just look from one to the other, and you know how relatively wide they are compared to each other, okay? So put them on the same axes. That's one rule. Second rule, align them vertically. Because, why vertically? Because you're comparing the x-axis, this one, right? And so you want to be able to look up and down the page and know that as you go from one plot to the next, that axis hasn't changed, and you can see things move left and right. And so you can see really quickly here, the disk is in the middle, inter is skewed to the left but occupies space that's to the left of the disk stars, and you can see that halo is actually shifted to the right and has a right tail as well. Okay, you're making all those judgments. They're all probably roughly located around 0, but they're spread differently. It looks to me as if the disk stars are not much spread at all. The intermediate stars are probably spread the most, and the halo stars, a little bit in between, are still pretty spread out compared to the disk stars. And you can make all those judgments really quickly looking at one graph, right? And it's not optimal to put them side by side, because side by side doesn't draw your eye down that page and see the relative locations of those three distributions, okay? And if you had 4 of them, you'd put them 4 down the page. You wouldn't put them in a 2x2 grid, because a 2x2 grid makes your eye go boom, 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 right? Makes a little Z or Z, depending on where you come from. That's no good. Your eye needs to go down, right? And so these are the judgments you have to make. And these are the choices you need to think about. Yes, sir? That is a great question. Why don't we worry about the y-axis? Because these are histograms, so the y-axis is the count, okay? These data sets have different sizes, so the count doesn't matter, okay? So you'd only mess with the y-axis if the count was something you wanted to compare between the 3 of them, and it's not in this case, okay? So the controlling that we're doing is all around the things we want to compare. That's an excellent question. Now, you can also use QQ plots to compare the distribution, but the rule is a little bit different. So let me show you how you would do QQ plots for this particular data set. So, first thing I'm going to do is I am going to go back to 1, 3. So laying them out side by side. Now, you might say, why side by side? For a QQ plot, the data axis is the y-axis. Okay, in a QQ plot, the theoretical quantiles are on the horizontal axis, the data is on the y-axis. So if you put them side by side, you'll be sweeping across the page comparing data, data, data. That's what you want to do. So side by side is right for QQ plots for that reason. You also want to make sure all your plots are square. So you want to do that. Okay, now we're going to put the plots down on the page. We've got to be a little bit careful. QQ norm of disk. Now, what do I need to mess with this time? I need the y-axis to be big enough for all of the data sets, right? I need it to be the same as I go from plot to plot to plot. What did we decide? We decided that the axis went from about -300 up to +250, But this time it's the y-axis, and the reason it's the y-axis is because it's the vertical axis that is where the data goes in a QQ plot. So QQ norm disk, y lim equals c minus 300 to 250. Then you probably want to put a title on it. Let's see if we can do this properly. So comma main equals QQ plot for disk. Okay. Then we put a QQ line on it, QQ line of disk, and then AB line, V equals 0, colour equals grey, then an AB line, H equals median of disk, colour equals grey again. Okay. So a plot appears. Now, at the moment it looks funny because my window has been designed for a long skinny thing, right? So now we need to design a window for a shorter fatter thing. So make it wider and make it shorter. And it'll start to look nice, right? Okay, so there's my disk stars. Now let's do my intermediate stars. Now all I've really got to do in here is change disk for inter everywhere it appears, right? So that's there. Oh, inter here, inter here, and so on. Inter, and one more spot. Inter. Okay. So you get the idea. There's the intermediate stars, and finally, the halo stars. So now I've just got to replace all these inters with halos. Halo, halo, halo. Halo. Halo, halo. Halo. And halo. There's the three of them. Side by side, now I can do the comparison, okay? Because the axes are the same, you'll always have these are lining up in the right way. You can see, again, the spread of these is much smaller. They're squished up here. The spread of these is bigger. The spread of these is up and to the right. And you can see curved here, curved down, pretty much straight. There's just an outlier. If that wasn't there, you'd say they were normal, okay? And there you have your plot. Now, one more thing. This is a great plot. This is what the sort of thing you should hand in. But wouldn't it be great if you could add a title to the whole thing, right? Because you've got titles on these separate things. So let's do that. So that's going to require us to redo it all, but that's okay. I can just go back here. When I go par mf row equals C13, okay, I'm going to go OMA equals, so OMA stands for outer margin. And what I'm going to do is I'm going to put a vector C. I leave 0 room at the bottom, 0 room at the left. I'm going to leave 2 lines at the top, and I'm going to leave 0 at the right. So they number from bottom, 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 left, top, right. And I'm just leaving some space at the top, right, so that I can put a title. Okay? So I just do that. Then I do my plots on the page. So PTY equals S, disk, inter, halo. The keen eyed among you will notice there's a little bit of room at the top now. Okay? And so I can put a title there. I go M text, stands for margin text. The text is going to be, here are my QQ plots. What a silly title. Okay? Side equals 3. So remember, numbers from the bottom. Bottom's 1, left is 2, top is 3. Okay? Side equals 3. Outer equals true. So I'm putting it in the outer margin. And I'm a showboat. CEX equals 1.5. I'm going to make it bigger because I want everyone to know. And there it is. Okay? And so now you've produced a plot that is pretty darn good, okay? Because you've made these choices. And we can compare these distributions now pretty easily. You've got a plot with the densities lined up, you've got a plot with the QQ plots lined up. You can say, are they normal? Where are they located? If they're not normal, what shape are they? Are their spreads different? Etc. So you can talk about all of those things. All right. Yes?
Is there any way to compare this law of the QQ line?
Well, visually you can just look at it. So if it's shallow, then it's shallow, and if it's tilted more, then it's higher. The slope is the standard deviation of the data, so you can calculate it. So you can work out what they are and you can make a numerical comparison. So you've either got the angle or you can calculate numbers. Those are your two choices. So, yeah. Angles are hard though, right? So, but, you know, you can tell that this line's pitched much more shallowly than this line, but it's even pretty easy to tell that this line is pitched a little bit more steeply than this one. So you can sort of see that their spreads are slightly... These two have spreads that are pretty similar, but this one's slightly more spread out. Okay, one more thing. So these are different tools you can use. Now there's one more tool I want to talk about. It's called a box plot. You might have seen box plots. Box plots are actually taught in primary school. And they're usually called box and whisker plots in primary school. We don't talk about whiskers anymore once you're grown up. It's just box plots, okay? So let me show you a box plot. Let me tell you what they are. So I'm going to make this big again. I'm going to scrub what's in it because I don't really want things to be square anymore and I don't want 3 things on a page and all that sort of stuff, so I'm just going to scrub it. Okay, what's box plot look like? Let's draw one. So let's do a box plot. Well, let me show you some made-up data. X is going to be R norm of 1,000, 0, 1. So I'm just going to generate 1,000 random normals and I'm just going to type box plot X, except I'm not going to put that dash in there. Box plot X. Oh, what's wrong with my fingers? There. Okay. I'd never be a good piano player. There'd be all these odd notes coming up all the time. This is called a box plot. So you've probably seen box plots before, yeah? Yeah? No? Okay, not talking. It's all good. I'll just assume you've never seen them before and I'll tell you what they are. If you get bored, it's your own fault. Okay, what is this? This is a picture of the data based on 5 numbers. Those 5 numbers are the minimum, the first quartile, that is the data point that's a quarter of the way through if you brought them into order. The median, which is the middle one. The third quartile, which is the 75% one, 3/4 of the way through, and the maximum. It's called the 5-number summary of a data set. Okay? The box is the middle half of the data. It goes from the first quartile, that's the 25% point, up to the third quartile, which is 75%. The reason it's a box in the plot is it emphasises the middle of the data, the middle 50% of the data. That's the stuff that matters. Everything else should be thought of as the tail. And so they produce these things called whiskers. Okay, these are the whiskers. Everything in a box plot has a name. The top and bottom of the boxes are called the hinges. We're never going to use these words, but they're funny. These things here are called the fences, right? There's all sorts of names for box plots. Doesn't matter. You get the idea. The box is the middle part of the data. The whiskers go out. You'll notice that the whiskers don't go all the way out. This is called an outlier box plot. The whiskers go out to a maximum distance of 1.5 interquartile ranges. In other words, 1.5 times the distance between the 2 quartiles, Q1 and Q3. Okay, that's just a rule. The reason that rule exists is that if you have a big outlier, if the whisker goes all the way out to the outlier, you don't really know whether there's much action out there. You don't know whether there's a lot of data out there or just 1 or 2 points. So they sort of stop the whiskers a reasonable distance from the hinge, and anything that's out beyond that just gets printed separately. It's called an outlier box plot. Okay? So this is a representation of the data, and you can imagine, right, so here you have to imagine a third dimension. So imagine the data, the distribution, it's basically coming out from the board, right? You've got the tail, and then it's coming out to a peak, that's the middle of the box, and then it's coming back into the tail on the other side. So the bottom is the left-hand tail, the top is the right-hand tail, and that's your picture. That's for normal data. Okay, that's for normal data. What's it going to look like for the intermediate star data? Let's have a look. Box plot of inter. That's what it looks like for the intermediate star data. What do you notice about this? It doesn't look like the one we just looked at, right? Because the one we just looked at looked really pretty, symmetric, because the box was in the middle and the two tails were roughly the same length. But that's because the normal distribution is symmetric. Its two tails are roughly equal to each other in size. We know for the intermediate star data, one tail's bigger than the other tail. We know that the left-hand tail goes down further than the right-hand tail. So you get a box plot that looks squished up at one end and extended at the other. So when you get a box plot that's got that sort of shape, you know you've got a distribution that's skewed down because the tail is down, skewed to the left. Okay? What about the halo? Pardon me. What about the disk data? Let's have a look at the disk data. What do you expect? It was roughly symmetric, but something interesting happens, right? It's sort of, you've got bad outlier. You spot that really easily now, okay, right here. Okay. What about the halo stars? Halo. Looks like that. It was skewed to the right, so it's got an extended whisker up to the right. Now, box plots work well when your data has one bump. Right? Unimodal data, box plots work okay. All right? One bump, box plots work okay. Two bumps, not so much. So let's look at that. Let's generate some data that's got two bumps. So I'm going to take a random normal. We'll generate a lot of data, 500, 0, 1. So we'll put a random normal at 0, and we'll ram that into a random normal at, I don't know, 500, 5, 1. So I've got two random normals next to each other. The histogram looks like this. Okay, so it's something like this yesterday. The QQ plot, we know what that looks like. It looks like an S shape, right? Yep, saw that yesterday. What about the box plot? Looks just like the box plot for a normal, right? And the reason is, there's a 5-number summary is all you get, right? If I've got two normals standing next to each other, how many numbers do I need to describe that? I need more than 5. I need to know where each of them is, how spread about each of them are, how split apart they are. I need a lot more information than just 5 numbers, okay? The median for this data is actually in the middle of those two distributions that I've smushed together, and it doesn't represent the data at all, right? So for multimodal data, box plots, epic fail. Okay? So before you use box plots, make sure your data is unimodal, or at least close to unimodal. All right. How do we use box plots to compare distributions? Well, this is awesome because R lets you do this. Box plot. Disk, comma, inter, comma, halo. Okay, names equals C, disk, why can't I spell? Disk, comma, inter, comma, halo, and you get this picture, which is some kinda awesome, right? You get side-by-side box plots, and the names I gave it, names equals, they go down the bottom. They tell you what the distributions are. This is a pretty good display. These are all unimodal distributions. Their bumps are in different places. You can see that. If you cast your eye across the page from left to right, you can see where they're each located. You can see the spread characteristics of the three distributions pretty easily, and you can see the shape characteristics of the three distributions pretty easily. So this is a nice plot for this data. Not for every data set. If you've got multimodal data, you're out of luck, right? But that's you know, horses for courses. All right, that's box plots. If you look in the notes, there's some, you can see how to make all these things look super tidy and all that, right? Putting titles on and everything, so I'll let you look at that. Because again, watching me type it cannot be any fun for anybody at 2 o'clock on a Wednesday. But the main message here is we've now got a bunch of tools for displaying one-dimensional data.